introduction. And here the product is road lenses, what we use for traffic lights, road signals, and the pavement paths where we from safety hazards. So there are 13 predictors and one response variable, and which I'll be talking about 4 different quality class categories, and there are 13 process variables in which it is an ordinal category of quality class. The class 1 is the least, the class 1 is the defective one, the class 2 is acceptable, class 3 is the true value we need, and class 4 is the inefficient one which we need to be more work done to be here. And here are the data set on the right side. We see the data set overview. There are the variables and data values. So there are 3 major questions which we will be working on. And so here you can see the 4 different quality class categories, and the quality class 2 and quality class 4 shows the higher value. The quality class 2 is the acceptable quality where we have major amount of products, but our primary focus is the quality class 3. I know it's very difficult to understand between the quality class levels, as the highest the quality is, the better the product is. But here the quality class 3 is the preferred one. Here we can see the correlation, as the correlation has a very distinct correlation between different variables, and it's basically higher performing classes, especially classes 1 and 2, exhibit tighter distribution in clamps, forces, and injection pressures, suggesting more consistent operation and better control of cavity packing. Relating these factors to the class definition clarifies the quality scale. And also here we can see the different all 13 variables showing their variance in their data set. We can see the cycle time, fill time, and injection has very vast variation between the data set, and all the other values, all the other variables has very stable kind of variation. And basically this data was collected by a company in Spain, and they showed over a span of time, or a different span of time, how the different variables affect the injection molding cavity. The quality classes has like the defect ratio of showing like it fails on in between. If it's less than 0.4, then it's if it's between 0.4 and 0.5, then it's like acceptable, and it's like it depends. The 0.45 to 0.5, then it's like in class category 3, and then it's class 4. If it's better than 0.5, then it's class category 4. Here we can see the summary of all 13 variables, showcasing the mean, median, and mode. What I used for using the method was a multinomial regression analysis, as we have 4 class categories. I used class 1 as the baseline to analyze the data, and class 2, 3, and 4 are the relative levels. The 13 variables what we used, in which there was 70% training data set and 30% test data set, in which in the training data set we have used the quality class 1 products, that is 370 products, 406 of class 2, and 310 of class 3, and 360 of class 4, in which we have characterized as this data set as 111 of class 1 and 134 of class 2, and then vice versa for the other quality class here I used the performance matrix as like the major criteria I used was accuracy, sensitivity, and specificity to look for the variables that affect the most for better analysis. For the first model, I used all of the variables, and when we look at all the variables, they are based on their peak value, where we see that it has the melt temperature has like very high peak value, but when I remove the melt temperature from the second model, the accuracy was not very well. But when we look at the model, class 3, the melt temperature has a very good p-value, but the other two variables, torque mean and torque peak, have higher p-value. High p-value, which show that if I remove these two variables from class 3 and class 4 that has very high p-value, it made the accuracy 1% better, but it did not really increase very well. So I was looking at that, and when we look at the confusion matrix, we can see the probability of choosing the confusion matrix for model 1 was good, but when we look at the confusion matrix of model 2, it made a very big, not very big, big effect, but it made a very gradual effect on that. The accuracy for the model 1 was 82, but the accuracy for the model 3 made a little slightly better, that is 0.83. And when we look at the sensitivity and specificity, for the model 1, it was around 90%. All of it was 90%, but in the same case as accuracy, it increased by a little 5 to 6% of specificity and sensitivity. And when we look at the model comparison, we look at the AIC values. Both of the values have very low AIC, but the stable. When we look at the lower AIC, it's the likelihood ratio is better for both of them, but it's very stable. The model 2 is very stable and it's slightly higher. The accuracy is slightly higher, and because of the reduced model maintains strong predictive metrics while removing the unnecessary variables, it provides a practical and efficient model for the classification. We can always use more different kind of models like random forest model to make it more accurate, but I was using a similar model what we use in our classes. This is in the limitations. Basically, the limitations were it was highly effective of the variables I was using for every single model. Every single variable was highly significant, but whenever I was using removing different kind of variables, it was showing a similar kind of effect on all the categories, on all the models. Finally, the model shows a strong accuracy and class-specific metrics. It may classify some borderline or overlapping cases, especially among classes with similar characteristics. In conclusion, this enhances prediction reliability while maintaining simplicity. The model serves as an effective tool for multi-class classification, offering very valuable insights for decision making while highlighting the needs for ongoing evaluation and possible refinement as new data